Alright, we have an interesting situation here. One of my kittens just decided that it was my true and beloved friend, and it came walking across the desk here, stepped on the computer, and I didn't realize it. It turned off the camera. And so I just did this entire lesson and it didn't record. So now I'm going to have to do it over again, and I just can't bring myself to rewrite everything. So we're going to do it the lazy way. Alright, we're talking about solutions now. And I gather that this is something that you didn't cover in 10th grade chemistry to any great extent. Now, you probably had some practical experience with solutions. So let's begin with the vocabulary. And the thing to be careful of here is that so much of the vocabulary begins S-O-L. And so that makes it easy to confuse one word with another. You can't use the middle school technique of learn the first syllable and that will be enough. It won't be enough. There's just too many of them with the same beginning. For instance, the word solution itself. A solution is simply one substance that's dissolved in another substance. Well, you have lots of experience with that. Kool-Aid, ocean water, sugar water, just lots of experience with that. But when you start thinking of it in terms of chemistry, what do we mean by dissolved? Well, in the ordinary course of life, if we dissolve sugar in water, the sugar disappears. You can't see it anymore. It's gone. And yet you know it's still there because if you taste it, there's the sweetness of the sugar. The sugar is still there, but it's invisible. So what's happened here? Well, what has happened is that one substance has separated into individual molecules if it's a covalent compound, or into individual ions if it's an ionic compound. And then those teeny tiny little particles have spread out uniformly among all of the other molecules from the other substance. The reason you can't see it anymore is because you can't see individual molecules. They're too small. And you certainly can't see individual ions. They're too small. But they're still there. They're just very, very, very tiny. So here's sort of a picture. The little Mickey Mouse heads, of course, are water. And here are sugar molecules, and I'm not even going to attempt to draw them realistically. They're far too complicated. But you can see how the sugar molecules have separated from each other. None of the sugar molecules are stuck to any other sugar molecules. And they've spread out so that they're evenly but randomly dispersed among the water molecules. Now, in order to keep them spread out like that, we have to have the formation of some van der Waals forces between the sugar molecules and the water molecules. But we'll go into that in a minute. All right, the substance that separates, the one that becomes individual molecules or individual ions, is called the solute. And the one that doesn't separate, the one that stays the way it was, is called the solvent. See all those SOLs? Kind of annoying after a while. So in this case, the sugar was our solute and the water was our solvent. Now, we tend to think that solutes are solids and we dissolve them in liquid solvents, but that's not necessarily true. We can dissolve gases in liquids, the carbonation in a Coke. We can dissolve solids in liquids, well, like the sugar and the water. We can dissolve liquids in liquids. We can dissolve alcohol in water or water in alcohol. It goes either way. We can dissolve gases in solids. We can dissolve solids in other solids. That's what an alloy like white gold is. It's one metal dissolved in another one, separated in right down to the atomic level and spread out among the crystal of the other metal. So it doesn't have to be a solid solute in a liquid solvent, but it very, very often is. Now, there is a limit to how much solute will dissolve in a certain amount of solvent at a certain temperature. And that limit is called the solubility. It's the maximum amount, the maximum number of grams of solute that you can dissolve in a certain amount of solvent, say 100 milliliters. That's a very common amount of solvent for expressing solubility at that particular temperature. So maybe we can dissolve 100 grams of this solute in this solvent at room temperature. If we have that full amount, if we've dissolved all 100 grams in that 100 milliliters, then our solution is saturated. It's holding all the solute that it possibly can. It can't hold any more, at least not at that temperature. If we have less than that maximum amount, then our solution is unsaturated, and we could dissolve more solute in it if we tried. We don't have to, but we could if we tried. It's even possible, if you are very, very careful, to produce a solution that is supersaturated. And supersaturated means that my card is full. No, it doesn't. It's still going. Supersaturated means that this solution contains more than the maximum amount of solute that will dissolve. And you go, wait. How can you dissolve more than the maximum amount that will dissolve? It doesn't make any sense. Well, you can do it if you're very careful. Say that our solubility at room temperature is 100 grams in 100 milliliters of solvent. But if we warmed up our solvent, boiled it maybe, we could dissolve 200 grams of solute in that same 100 milliliters of solvent. So let's do that. We heat it up, we boil it, we put in the 200 grams, we stir it all up, and it's dissolved. Turn off the heat and be very still. Don't pick up the container and move it to the side, because the thump when you put it down will mess things up. Just let it sit right where it is and cool off very slowly. And sometimes you will manage to keep all 200 grams dissolved even after the solvent has come back down to room temperature. It just didn't notice. It's the classic case of, throwing the frog into the water and gradually changing the temperature, and he's cooked before he knows it. He could have jumped out at any moment. He just didn't notice that there was a problem. Well, this solution just didn't notice that it shouldn't be holding on to that much solute. Now, that excess solute will precipitate out if you jiggle it or thump it or do anything to it to make it move around a little bit. Or if you take a file and reach into the beaker and scratch the inside of the beaker, that will do it. Or if you take one teeny tiny little crystal of solute, solid solute, and drop it in. That one little seed crystal will get the formation of crystals started, and all that excess solute will precipitate out in a matter of seconds, like maybe 1 or 2 or 3. Very, very rapid. And that's pretty cool to see. Remind me to show you sodium acetate. That's just too cool for words. It's really fun to play around with sodium acetate. The nice thing about it is it's fairly easy to get it supersaturated, but still very dramatic when it decides to go back to being just saturated. Occasionally we'll run across a couple of materials, a couple of substances that are immiscible. It looks like a terrible, terrible word, but M is just like in or un. It means not. Miscible is just a funky spelling of mixable. They are not mixable. They don't like each other. And so they won't dissolve in each other. They just won't. What's happening, of course, is that we're not forming strong enough van der Waals forces between the solute and the solvent. And with nothing to hold them to each other, they'd rather stay with their own kind. Here's a comparison. Suppose that Carrollton High decided to invite the Oak Mountain High School students to the Carrollton High prom. Who knows why? And we decide that it would be good manners to go. We don't really want to. We'd rather have our own prom. But they invited us, so we'll go. All right, so the Oak Mountain kids get to the Carrollton High prom. And a lot of the Oak Mountain kids know some of the Carrollton High kids, maybe from church or from the neighborhood. And so there's a few conversations. There are a few conversations just being polite. Oh yes, thank you for inviting us to your prom. Maybe even a few dances. But within half an hour or so, I guarantee you, the Oak Mountain kids will be on this side of the gym, the Carrollton kids will be on that side of the gym, and there'll be very little interaction between the two. The Carrollton kids have got their friends, and of course they want to hang out with their friends. The Oak Mountain kids have got their friends, and of course they want to hang out with their friends. And there may be a little crossing back and forth, but by and large, they won't mix. Well, it's the same way with immiscible substances, and you've actually seen this happen with oil and water or vinegar and water. Water will bond, well, it will not bond, it will have strong van der Waals forces holding it to more water. Water molecules and water molecules are attracted by dipole-dipole attractions because the water molecule has a partially positive end and a partially negative end. They will be held together by hydrogen bonding because we have a hydrogen atom that's attached to nitrogen, oxygen, or fluorine. And so that hydrogen atom is going to be attracted to the lone pair on that nitrogen, oxygen, or fluorine. We're going to have London forces caused by that temporary imbalance of electrons that causes a temporary dipole. So water molecules love other water molecules. Well, the oil molecules get along pretty well too. There are no dipole-dipole attractions because they're not polar. There are no hydrogen bonds because we don't have hydrogen atoms that are attached to nitrogen, oxygen, or fluorine. There will be London forces, however, and oil molecules are long molecules. There's lots of atoms along the length of that molecule that can get their electrons off balance and be, just for a flicker of time, partially positive or partially negative. And when you add up all those little temporary flickers, it turns out to be a significant attraction between one oil molecule and another oil molecule. But when you put them together and try and stir them up, the oil molecules and the water molecules just really don't care for each other. There won't be any dipole-dipole attraction. There won't be any hydrogen bonding. There won't even be much London forces because while the oil molecules are long and can form lots of London attractions along their length, the water molecules are teeny tiny little molecules and they can't do that. So there's going to be very, very little reason for them to stay together, and pretty doggone significant reasons for them to stay apart. So when you mix them, set them down, they separate. The oil floats to the top, the water stays on the bottom, and they just won't have anything to do with each other very much. That's why when you have an oil and vinegar dressing, you have to shake it up right before you pour it on your salad because it's just not going to stay together for very long. All right, that pretty much gets us through the introductory vocabulary, so let's stop for right now.